Let us now formalize conditional probability and see if we can get a formula for us to easily compute conditional probability. Now, let's have a recap. We are considering the throw of two fair dice, and we were asked to find the probability of getting a sum of 7 given that the digit in the first die is greater than that of the second. Now, we have considered that we actually have two events happening. The sum of 7, and the one that already happened is that the digit in the first die is greater than that of the second. So let's take a look at our outcomes and see what we can figure out with the two events that happened. Let's just zoom that in. There you go. And here. So the events that actually happened are the ones in blue, which is the probability that you're going to get a sum of 7 when you throw two fair dice, and the one in green, which is the probability of when you throw two dice, the digit in the first die is greater than the digit in the second die. This purple line here represents the probability that we actually wanted to solve, although it's a bit cut because we zoomed in. So as we can see here, those that are part of what we wanted, the probability that the sum is 7 given that the first die is greater than the second die, as you can see here, is actually both in event green and event blue. Or, in other words, it is the intersection of these two events. So, if we would get that, let's just use a different color. For example, the probability here, if we get this intersection here, the probability of getting a sum of 7, and then, not and then, but and, the probability of the first die, the digit in the first die is greater than the digit in the second die, there you go, would be this 3 out of the total of this, which is 36. So we get 3 out of 36, or in simplest form, or in lowest form, 1 out of 12. So there. And we know this because we know that we can relate probabilities to our sets. So there. Now, like what we mentioned, conditional probability is on the idea that we are limiting our original sample space to the sample space of the condition that happened before, which would mean this one here. The probability that the digit on the first die is greater than the digit on the second die. And we know that there are 15 cases of those as seen here. So here you go. So if we will take note of that, the probability that the sum of the first die, the digit rather of the first die is greater than the digit of the second die would be actually 15 out of 36, or 5 out of 12 chances. This would be our now basis for our new probability, which is provided this happened first, we want to know what are the chances of getting these ones, which is the probability of sum of 7 and the first die is greater than the second die here. In other words, we want to know the probability of this happening out of this happening, and we usually express in terms of probabilities that as a fraction. So we write this one again. The probability of getting a sum of 7 given that the first die is greater than the second die would be essentially this probability happening out of the condition that it will happen. We want to figure out what are the chances of this probability, or of getting this probability out of this probability. And once we simplify this, we're actually going to get 1/5, which is, if we're going to zoom out a little bit, there you go. Well, that's not a little bit, but anyway, move that up. As we can see here, we have the same values. This will now lead us to the formal definition of conditional probability. So, let E be an arbitrary event in a sample space S with the probability of E greater than 0, meaning it is to happen. The probability that an event A occurs once event E has occurred, or the conditional probability of event A given E, written in this notation, is the probability of A given E would be equal to the probability of A and E divided by the probability of E. As we illustrated a while ago, we see here that the probability of the conditional probability that we got is the probability of the intersection of the two events, the condition and the event A that we want, out of the probability of the condition that happened already. So there you go. So let's practice using this formula. Let E and F be events in a sample space. Let's just move that a bit. There you go. So suppose P of E is equal to 0.6, P of F is equal to 0.7, and P of E and F is equal to 0.3. We're asked to find the value or solve for the value of the probability of E given F. So again, our formula is the probability that E given F would be equal to the probability of E and F all over the probability of F. And we have those values here. The probability of E and F is 0.3. The probability of F is 0.7. So 0.3 divided by 0.7 will give us 3/7. So the probability of getting the probability of E rather given F is 3/7. So the second one, suppose the probability of E is 0.65, the probability of F is 0.75, and the probability of E union F is 0.9. We're asked to find the probability of E given F. So here, remember again that the probability of E given F is equal to the probability of E and F all over the probability of F. In this case, we're given with E union F, but we know from the general addition rule, there you go, we know from the general addition rule that the probability of E union F is equal to the probability of E plus the probability of F minus the probability of E and F. Manipulating the general addition rule will give us the probability of E and F is equal to the probability of E plus the probability of F minus the probability of E union F. So therefore, the probability of E 0.65 plus the probability of F 0.75 minus the probability of E union F, which is 0.9, which gives us 0.5 or 0.50. So therefore here, the probability of E given F would be 0.50 all over the probability of F, which is 0.75, which would be equal to 2/3. So therefore, the probability of E given F would be equal to 2/3. So this formula here can be our guide when we solve problems involving conditional probability.